Thanks, and thanks, Gediminas, for organizing this really delightful Humboldt colleague. And in particular, he had to work extra hard to arrange my talk to be on my birthday. So thank you for that as well. Aw, shucks. So, I want to tell you a story about Rydberg molecules, introduce you a little to the subject, because there has not really been much discussion of Rydberg systems so far at this colleague. I'll give a brief review of some of the theory and experiment in that area, and a new idea we have that is going to be published in Physical Review Letters fairly soon. This work is done by a graduate student who just finished a couple of months ago working with me, Matt Eilis, now a postdoc in Dresden, and Jesus Perez-Rios, a former postdoc in my group. We've collaborated at various stages recent years with Herwig Ott's group in Kaiserslautern and Tilman Pfau's group in Stuttgart, and I'll mention some of that work. So, basically, there are two themes to this talk. One is what still kind of is captivating to me mentally is this unreasonably powerful effect of a short-range phase shift in many different contexts of interest to this community. And the second point is the really strongly non-perturbative implications of high degeneracy. So with that, I'll describe, most of the talk will be about this Rydberg molecules and what we're calling their ghosts. And if I have time, I'll say a little bit about Efimov physics with a charged particle, a kind of a different regime that has never been studied experimentally with Efimov few body physics. If you'd like to see some recent reviews, there's a very recent one by Jim Schaefer, Seth Rittenhouse, and Hossein Sadegpour in Nature Communications on the ultra-long-range Rydberg molecules. And there are a number of recent reviews, including one by Shimpe Endo, who's here, and a former postdoc, Jose Diancao. And we had a review of Modern Physics last year on few-body Efimov and universal physics. And especially we're interested in these systems of very large scattering lengths or scattering volumes, as I'll show you. So again, I want to emphasize especially this common thread through basically it's permeating all of the subjects of interacting atoms with ultra-cold systems, both few-body and many-body, is that the particles are dilute, the de Broglie wavelengths are long, and the particles are mostly free, but they are occasionally colliding. And every time they do collide, there is a short-range collision, the wave function acquires a phase, and that phase can be translated into an energy effect, and that was done by Enrico Fermi. Every such collision with one of these particles, whether it's in a BEC or a degenerate Fermi gas or a few-body system, has this energy effect. And we like to summarize that energy effect with the Fermi pseudopotential, a zero-range potential controlled by the energy-dependent scattering length for S waves. And in some contexts, and it turns out especially important in ultra long-range Rydberg molecules, the P wave can be extremely important as well. And they're controlled by the S wave scattering phase shift translated into a scattering length, or the P wave scattering phase shift translated into a scattering volume. So this, as you know, you can, using these types of interactions, you can derive the Gross-Pitievsky equation for BEC, the mean field equations and their generalizations into Bogoliubov theory and effective field theory. And in few-body physics, it generates the Efimov effect, It's relevant to nuclear physics in the unitarity limit of almost infinite two-body scattering lengths, and what I'll discuss next, ultra-long-range Rydberg molecules. So when you apply that Hamiltonian, that interaction Hamiltonian, to a Rydberg atom interacting with a ground state neutral atom, and in some particular, like an alkali atom in a state of effective quantum number nu, shifted from the integer by a quantum defect, and orbital angular momentum L, typical one electron wave function like that for a Rydberg electron. First order perturbation theory just says, well, basically the wave function stays the same, but it implies an energy of interaction. And in particular, for negative terms, you can get an attractive interaction with the ground state atom and this Rydberg atom. And it is a weird-looking Born-Oppenheimer potential energy curve that oscillates just like a wave function. And this surprised us at the time. But we predicted that you could make spectroscopic observations of bound vibrational states in those strange potentials that I'll show you in a minute. It took several years, but eventually some groups led by Tillman Fow's group first, and now several other groups have observed these kinds of strange ultra-long-range Rydberg molecules whose binding bond lengths can be more than 1,000 Bohr radii. And so this is what, for instance, if you take a 30D state of rubidium and interact with a gas of ground state atoms, you see potential energy curves like this with quantized vibrational levels in the outermost well. The first observation by Tillman Fow's group was not for a D state, it was for an S state, but the same basic logic applies. And you can see the ground state, or rather the Rydberg S wave function, and the resulting potential curve is kind of faint over here with the vibrational states that they observed in the spectroscopy redshifted from the atomic line. Since then, other groups like at ETH and at Michigan and at Rice universities have also seen these kinds of states. This is one of the experiments that I was always impressed by, where they could see changing the quantum number of the Rydberg atom from 50-ish to over 100. You can see the evolution of different levels, and even like a dimer, trimer, tetramer, pentamer. You can see this sequence of states eventually smearing out into kind of a smooth mean field shift when you have many, many atoms in the Rydberg orbit. And there's been some nice theory work in a couple of years ago by Schmidt, Sadeghipour, and Demler, which gave a nice interpretation, for instance, comparing with the N=71 spectrum, and developed some nice techniques for handling that physics. So, you know, as a theorist, I have to say it. Perturbation theory, first order, non-degenerate perturbation theory is about as boring as it gets, okay? It's just not very interesting. The wave function just sits there and it doesn't change, okay? And, but systems with a high degeneracy, even when you treat that high degeneracy in degenerate perturbation theory, can respond and change the wave function to adapt to the nature of the perturbation. And in that sense, I mean, there are famous examples of this, like the fractional quantum Hall effect, where you have this exponentially or factorial large degeneracy, and you see these really fascinating types of states like the Laughlin states and so on. In that sense, I like to say that degenerate perturbation theory, systems described by that when the degeneracy is high, is really non-perturbative, because you have a big Hilbert space and the wave functions rearrange and do something to feel that. And in the Rydberg molecule problem, you have this situation because the high orbital angular momentum states are effectively degenerate and have zero quantum defect. And the implication here is that this low L type state, which has only maybe a 10 to 100 megahertz well depth, now this goes to 10 gigahertz when you do the same principal quantum number, but with the high L states that have this high degeneracy. And moreover, the wave functions rearrange from what we're normally used to thinking about for hydrogenic atom wave functions. They rearrange to make something that really feels and puts extra electron density on top of the interaction in the problem. It took longer to observe these because these high L states are harder to excite from a ground state, but they were eventually seen in the Schaefer group in Oklahoma in 2015, these types of trilobite molecules. Another thing that can be important in these problems is the P-wave scattering phase shift, and it even has relativistic or spin orbit splittings, especially for the heavier atoms like cesium or rubidium. I think in the interest of time, I will just gloss over this quickly, except to say that we did generalize in a PhysRev A paper last year this Omont P-wave pseudopotential to include the spin orbit interaction, if any of you are interested in building in that kind of spin orbit physics. And this was just a test of our treatment that agrees well with a more complicated Green's function treatment. But one of the things that's interesting about these is you see these plunging potentials, which we call the butterfly states, because, and these are associated with the P-wave shape resonance in electron rubidium scattering. And this is the reason we call them butterfly states, because they have wave functions that have this sort of butterfly or dragonfly sort of shape. And these also took a long time to observe, but they were seen in spectroscopy by Hervé Gott's group in 2016. These wells near this P state, which borrowed enough dipole oscillator strength to be excited from the ground state with one photon. And you could see these vibrational levels in this range of internuclear distances with hundreds of dBi up to sort of half a kilo dBi permanent electric dipole moments. And this is a Stark spectrum proving that the states they were seeing did correspond to these high permanent dipole moments. So one thing that intrigued us along the way was the fact that these strong electric dipole moments could be maybe interesting in a one-dimensional lattice environment. So for instance, if you make a one-dimensional cigar-shaped gas, basically, and you excite one of these atoms or one of these molecules with a strong dipole moment, it would have a long-range blockade that would normally prevent exciting anything nearby. But if you arrange this at what used to be called the magic angle, this 54.7 degrees, where the dipole-dipole interaction cancels, you can make an order of magnitude more dense. And so you have control over the density of the lattice, if you like, of ultra-long-range Rydberg molecules that you can make this way. Okay, so let's come to what we're calling the ghost trilobite chemical bond. Okay. And as I mentioned earlier, this is on the archive, and it is a PRL that I just learned 2 hours ago has been accepted for publication. So one of the interesting things I've been stressing, this is coming out of degenerate perturbation theory. You're superposing degenerate orbitals. They can be superposed without any energy cost, and any linear combination of these degenerate states is still an eigenstate of the Hamiltonian. And it will be a stationary state. It stays there forever if the degeneracy is exact. And in particular, the trilobite state, say, or the butterfly state, or any state you want to make, is even a stationary state of this Schrodinger equation, even if there's no distant ground state atom. And so that means we could simply engineer this chemical bond even if there's no atom to bind to. And so basically, we set out to do that, is to find a sequence of electric and magnetic field pulses which will warp an initially maybe laser excited S state, warp that in a hydrogen atom into a trilobite chemical bond, reaching out into the vacuum to nothing. So our first attempt was, well, we thought, well, we can just feed this into a random number generator and we could find the sequence of pulses. Well, it didn't work so well. This is like the exact n equals 10 trilobite molecule wave function. And if we do this random kind of sequence of electric and magnetic field pulses, we could only make this sort of weak cousin to this baby trilobite, ghost trilobite, which was only maybe 80%. But we found that if we used the ideas, if we adopted some of the ideas from machine learning, in particular the simplest idea, gradient ascent algorithm, then we found we could, in fact, find a sequence of controlled field pulses which deterministically makes this as accurately as you want. And in particular, we've tried to foresee some of the experimental difficulties and proposed how we would recommend doing this. N equals 70 is a pretty good example, principal quantum number. And we realize it's hard to switch magnetic fields very fast, so we set this up where there would be a relatively slow static magnetic field ramped on up to around 100 Gauss, but then that would be held fixed until an end ramp. And then a sequence of faster electric field pulses, but with variable time intervals that are optimized to give the highest overlap with this trilobite or other chemical bonds. So this is kind of the way it looks. You first excite to this S state, now you ramp on the magnetic field, and you're making kind of a different state. Again, it's just an eigenstate of the hydrogen atom, but a different linear combination than you're used to thinking about. Then you apply your electric field pulses, and then you ramp off the magnetic field, and at the very end, you've got the trilobite chemical bond, except without an atom that's actually binding to. It's like a preformed chemical bond, if you like. You might imagine doing something like bringing another atom into that chemical bond later. And we've proposed some schemes, possible ways to detect it, like, oh, by the way, the trilobite you're used to seeing is it's a surface of rotation. And so you're used to seeing it this way, but this is the same object actually displayed as an isodensity surface in real space. This is some details about the evolution. Maybe I don't get into that or that. Just to maybe show you, you can make different types of states. This would be the trilobite with 3 inner angular nodes, and this would be a butterfly state you could make. And basically, we could make these to 99.99% fidelity. You could also make a trimer trilobite, where it's like a trilobite bond on both directions. You could make a Stark state if you like. You could make the elliptical eigenstates if you wanted, which might be closest to a Keplerian ellipse. But for the detection or observation, how would you know you made this bond if you made it? There's no energy shift now because it's not interacting with the ground state atom, but the wave function could be observed in E2E spectroscopy, which is basically measuring the momentum space wave function. Or you could do X-ray diffraction to measure the Fourier transform of psi squared. So let's see, do I have a minute or two? Okay. I will just say that in FMR physics with 2 heavy particles and 1 very light particle is much more observable and has a really interesting energy spectrum. It gets denser, or in the scattering length where it's usually observed. And an extreme case, which has been proposed previously, that we've looked at in detail in this archive preprint with Huili Han from China, who collaborated with us, is that you could see a very dense kind of FMOV spectrum, say for 2 rubidium atoms and an electron. There is a whole Hilbert space of states that's never been probed before, as far as I know, in experiment, and I think would be really interesting to see. There are more details in our preprint, but I think I'm out of time. Basically, I might just say that the usual FMOV scaling factor is now changed from something like 22.7 to 1.02, relating successive FMOV states. So with that, I'll just put up my conclusions and let you read them. Thanks for your attention.